Okay, this lecture is optimization unconstrained. The next lecture will be constrained optimization, which is associated with Lagrange multipliers. So, unconstrained. In single variable calculus, let's say our unconstrained function, so it goes from minus infinity to infinity, there's no boundary here. Let's say it looks like this. So we're interested in local mins and maxes, not global. So here we have a maximum and here we have a minimum. Now, where do these critical points, how do we determine where these critical points appear? Well, we take the first derivative and set it equal to 0. Now, technically, if the first derivative is undefined, that's also a critical point, in which case we would be talking about things like this. But let's ignore that for now and move on to the case where first derivative is 0. So what do we mean by a local maximum? Well, if you observe that the first derivative is positive here and negative here, then the second derivative goes from positive to negative, so the second derivative is negative. So we associate this fact with maximum, local maximum. Similarly, if we go from negative first to positive first, then the second derivative is positive and we have a minimum. Now, the second derivative could be 0, in which case we don't really know. Could be max, min, could be a point of inflection, it could be none of the above. And just, if you recall, point of inflection looks like this. You have something that's concave down, and then here's your point of inflection, and then it turns into concave up. So from the left, it's a max, and from the right, it's a min, so it can't really decide. We call that a point of inflection. And the example is y is equal to x cubed. Okay, again, this is unconstrained. If it were constrained, then we would just, limit the domain. And that's the next lecture. All right, moving on to multivariable calculus. Here the picture is a bit more complicated. So we have, say, a surface, and this surface has, well, mountains, let's call it, and say upside down mountains. So, and it also has things like, hard to draw, but things that are concave down, but at the same time, they could be concave up. So we call these saddle points, PDLE. So let's see how to figure out where these things occur. Well, here's a local maximum. So we have a tangent line, but we really have two tangent lines, one in the x direction, one in the right direction. So more properly, we think of this as a tangent plane, and a tangent plane, and a tangent plane here. Okay. So, critical points. Well, it's not first derivative is equal to x. It's both derivatives equal to x. So we call that the gradient of f. By definition, fx, xy. So we're looking for critical points. So we set it equal to 0, both of them. So this is the 0 vector. Now again, we have critical points that are associated with, sharp peaks and things like that. That's where the gradient is undefined, but let's ignore that for now. So this is equivalent to this. So now we need to look at the second derivative. Well, there's 4 of them. Here's the first derivative with respect to x, and then we do it again with respect to x. So here's the second derivative. But you also have, and I'm going to write it here, fy y, and you have fxy and fyx. These are called these two are called the mixed partials, and they're equal. We have a theorem that says this is equal to this under the assumption of continuity and differentiability. So this is a 2x2 matrix. We call it the Hessian Matrix. And if you take the determinant of this 2x2 matrix, and we'll call it D, capital D, or some books call it capital H, because it's associated with the Hessian. And how do you write the determinant? Well, it's this times this minus this times this. So let's write it up here. We have f x x f y y minus f x y, but these two are the same, so typically we write f of x y squared. Okay. So we're moving on to our second derivative test for multivariable. And we have 3 cases. D is greater than 0, D is less than 0, and D is equal to 0. Remember, this is just a number. This is a scalar. So let's look at D equals 0. And that's really equivalent to the double prime is equal to 0. So in fact, we don't know. Could be max, min, could be a saddle point, could be none of the above. Okay, let's move on to when D is negative. Here's D. This is necessarily negative. So here what we're saying is this number dominates. Okay, now there's a few cases where that could happen, but let's take the simplest of cases. So I'm not really doing a proof here. This is sort of a high-level idea behind the intuition of why all of this works. So this is necessarily negative. Let's make this negative, which will ensure this case. 2 possibilities. This could be positive, and this could be negative, or vice versa. So what does it mean for the second derivative with respect to x is positive? It's concave up, so it's a minimum. But what does it mean for the second derivative with respect to y is equal to is negative? Well, that means it's concave down or a maximum. So which is it? Minimum or maximum? Well, that kind of looks like what we call a saddle point. And that is, in fact, true. And if you reason negative, positive, same thing. Just reverse the order of your logic. So again, this is not a proof, but we're trying to get the idea of why all of this is true. Now, when D is positive, there's 2 cases. So this means this number dominates this number and is positive. Okay, this is a bigger number than this number. So this has to be both positive or both negative and sufficiently large. But we're not going to worry about that case. Let's just look at what it means for both of them to be positive. Well, with respect to x, the second derivative is positive, so it's a minimum. And with respect to y, it's also positive, so it's a minimum, no matter how you look at it. So it's likely, you can say that f of xx or f y is positive, then it's a minimum. And of course that's equivalent, or not equivalent, but similar to the single variable case. And it doesn't matter if it's xx or yy, because they both play the same role. Similarly, if f of x is negative, then we have a local maximum. And finally, if f of xx is 0, well, that means this is 0. So that means this is negative. That means d is negative. And that's contrary to our assumption here. So that possibility doesn't even exist. Okay, so there you have it. Not that hard, is it? This is the end of this lecture, and I do